All right, let's go ahead and start. So I think, at least in my head, we probably won't need that extra hour, but we'll see. Because we only have like 4 more reactions left, and they're smaller reactions. They're not too bad. This week in the discussion, this is where you're going to find your own article. And if you look at the rubric, it's found in the syllabus. It's basically the rubric we've been using each week, except not in pieces, the whole thing. Anyway, so if you look in the syllabus for the class under discussion, you'll see the full rubric. And what you're going to do is find your own article and analyze that like we've been doing, and you can follow the full rubric, okay? This week is your rough draft. So what you'll do is you'll turn it in. And I'll give you edits and everything. And for your replies, what you need to do is have suggestions on how they can make their critique, I guess you could say, better. Okay? So people are going to do a full article critique on their own, the best that they can. This is a rough draft. You guys will kind of all give them suggestions. I'll give you suggestions. And then the next week, or I guess it's not really the next week. You'll have to turn it in by Wednesday at midnight so I can get them all graded. Anyway, but by the next week, really, I guess it's about 24 hours later. Well, I can probably give you Thursday at like 10 a.m. or something. So about 36 hours later, then you can do like the corrections and stuff. Look at what I wrote on there that I suggest. Look at the suggestions of your peers, and then you'll correct it. Okay? So this is just so we can put everything together. Yes? The rough draft is going to be due next Tuesday, because that's probably going to be the one that takes the longest. If you do a good rough draft, your corrections won't be too bad. Okay? So that will be due next Tuesday. And then your final draft, I guess I can make it due like Thursday around 10 a.m. or so. I'll remind you when that comes up. Anyway, so that's for this week. Your sapling, you have 7 and 8 due this week. It'll help you to do them for the exam anyways. And then 9, because how the final falls, the final is obviously not tomorrow, but next Thursday. And so I have to have all the grades turned in that same day by 5 p.m. So really like right after this class, I have to go grade your final. Anyway, so the point is that I guess the sapling homework you won't have for Chapter 9 will have to be due like Thursday morning also. So a lot is coming up that's due, is what I'm getting at. So 7, 8, and 9 are all due pretty soon. So start on those. Yeah. The lab final is going, so that'll be released. Has it already been released? Can you see the lab final yet? Let me see. But it's, I thought it, so what today is when, okay, so it was released probably today. Let me check. And that is due the next Wednesday. So you should have a week to do it. Let me check. And Lab 10's vodcast is up. Let me know if you have any problems with it. So it's under coursework, just like the midterm was. And if you keep scrolling down, here's lab final. It says it's due Tuesday at midnight, and I think it's released. It looks like it is because it looks like you can see it since I can highlight it. So you had a week. You have about a week to do that. So it's very similar to the midterm that you did. So again, I went to the class, I go to coursework, and it's in Unit 6. If you scroll down, you'll see Lab Final. Just click on it, and it'll pull up to take it. Okay. Any other questions? Okay. Let's finish up Chapter 8. You have to review me today. So at the end of class, we have to fill these things out. Does somebody, I can't do this or I do it myself. Does somebody want to drop them off literally right there? You will? Okay, great. Just in, wherever the register, east. Oh, wait, no, they put it in. Just kidding, they need to be at E200. So anyway, so if you could drop those off, they won't let me. So. Okay, so let's look at this. Let's really quickly go over what we did yesterday. And I say really quick because we're going to review it again later. So, what happens when H3O plus is added across the double bond? What does that add on the double bond? OH. And is that Makarnikov or anti-Makarnikov? Makarnikov. What makes something anti? What do we look for? The peroxide, yeah. And can that one rearrange? Yes. That one can it'll form a carbocation. So how do we put an alcohol on there without rearranging? The mercury. So that's the one with the mercury, water, and NaBH4. Is there a carbocation formed there? Why not? The mercury, yeah. The mercury will take up both positions, making that kind of triangle. Do you remember what you put in a reaction if you want an anti-Makarnikov addition of OH? The boron, so it's the BH3, the OH, and NaBH4. Or I mean peroxide, H2O2. So the big thing you see is the peroxide, you can see that it is anti-Makarnikov. So BH3, and then hydroxide and H2O2 peroxide. Oh, and do you remember when we have the mercury one, how do those add? I'm not talking about the Makarnikov, but do they add a syn or anti, meaning on the same side or opposite side, the wedge dashes? Not on the same side, but the opposite side. So with the mercury, they always will add on the opposite side. But for the anti-Makarnikov, the BH3 reaction, they always add on the same side. What happens when I add Br2 across the double bond? 2 bromines, and do they add syn or anti? Anti. Do you form a carbocation in that reaction? Do you remember? No. It's very similar to the mercury one, where the bromine is going to take up both sides of the double bond, kind of creating that triangle. What happens when Br2 reacts with water? Br and OH. And do they add syn or anti? Anti. And then the last one, what happens when we add H2 plus our catalyst? It takes away the double bond. You add 2 hydrogens. And we'll go over that again, don't worry, in the review. I just want to quickly go over that so you kind of remember. So the next reaction I want to go over is actually the epoxide. Here. So slide 44 maybe for you? I'm not sure. So it's going to be epoxidation. 46? Okay, so first let me show you what an epoxide is. So an epoxide, kind of like an OH is an alcohol, a double bond is an alkene. This is just a functional group called an epoxide. And it looks like this in general. Do you see that? Do you see like this three-membered ring, this kind of triangle, with the oxygen on top? Okay? So it's an oxygen three-membered ring with two carbons. And that's called an epoxide. How you make an epoxide is like this. So you'd have like your double bond. And you're going to react it with what's called a peroxy acid. So I'm going to draw the general form of that and explain what that is. Okay. Okay, so you know a peroxide, right? The most common peroxide you're familiar with is hydrogen peroxide, which when bonded out looks like this. Okay? So you see that this part here looks very similar to the peroxide up here. Anytime you have the two oxygens bonded together, that's some sort of peroxide. And so you see we're doing a peroxy acid. That's where it comes. That's where that part comes from. Do you see that we have a double bond oxygen in there? So we have another oxygen. Okay? It makes this hydrogen even more acidic. So we call it a peroxy acid. Okay? So it's basically like a peroxide with a very acidic hydrogen, if you want. Not that it doesn't actually even act as an acid in this reaction, but that's where the name comes from. Okay, so this is going to form an epoxide. So I showed you what epoxide looks like. So what do you think the product will be? So I'm going to draw the same, basic skeletal structure. And then what do? So everything's going to occur where? Around the double bond, so like here and here. And then what does an epoxide look like? Yeah, the triangle, oxygen on top. So anytime you see something like this, you'll see the big thing for me, you're going to see the C double bond O, OOH. Okay, so this part right here. If you see that, that means draw an epoxide. And all you do, so you see that the double bond was right here? So erase the double bond and you put your oxygen there, connected to both sides. Which one? Where? I don't know what the notes say. Here? No, because this was a double bond. Keep the single bond. Okay, the most common peroxy acid that you'll use, we abbreviated MCPBA. This stands for meta, and I'll also draw this, chloro So MC peroxy benzoic acid. So all you need to, I just want to show you what the name is, and let me draw the structure, but you just need an MCPBA. Okay, it looks like this. Okay, do you see when I gave you the general form of epoxy acid? Do you see what I have circled? Do you see that in the structure? This C double bond O, OOH? That's what makes it epoxy acid. Do you see on the other side I just put R, meaning whatever you want? Okay, so this is your R group, and this is the epoxy acid part. So you see, all you need to do is recognize that C double bond O, OOH. Okay, that'll tell you it's epoxy acid. And the sapling homework, I've seen them do it both ways. I've seen them where they actually draw the structure for epoxy acid, so just look for this circle right here. And then I've seen sometimes where they just put MCPBA. Okay, MCPBA is epoxy acid. On the exam, if we have a question, and let's say it's a synthesis, and I give you this. Okay, do you see that I made an epoxide? Okay, you can write as your answer just MCPBA if you want. Oops, too many A's. MCPBA. You don't have to draw the structure if you don't want to. Now let me show you, it's not a mechanism you need to know, but let me show you kind of how this occurs so you can understand. Okay, this is the mechanism. So do you recognize right here? C double bond O, OOH. Okay, so that's the epoxy acid part. Now look at right here. Now anytime we form this triangle, do you remember we always do this? The double bond, in this case, is going to attack the oxygen, right? Because that's what's on there. And at the same time, the oxygen will attack the double bond. So anytime you form the triangle, so in your mercury reaction or your Br2 reaction, you form that triangle in your mechanism, and that's what's occurring here. So double bond attacks oxygen, oxygen attacks double bond, creating this triangle oxygen. Okay? Now let's look at our other arrows that are going on here. Do you see that this bond, where is it moving to? It's literally moving between the oxygen and carbon. So do you see it's breaking, so it's no longer bonded there? And then look at this double bond oxygen. What is it taking off? The hydrogen. Okay? So this whole entire area here, the rest of the molecule, is rearranging itself to leave. It doesn't want any part of that. And so the only thing that's left is oxygen right there. So the rest of the molecule leaves, leaving only an oxygen as that three-membered ring. And that's how the mechanism occurs. I'm not going to make you duplicate that, but I just want you to kind of understand how the epoxy acid makes the epoxide. Okay? and this is just showing you, it keeps the stereochemistry. So it's very simple. So do you see that this is a cis double bond? Okay? If we put MCPBA in there, what does it do? What do we put on there? The epoxide, a three-membered ring. And do you see that we just keep the CH3s pointing the same direction? So however I draw the double bond, just keep it that way. So that's what we've been doing. So do you see how I drew it like this? Okay? And then I basically redrew it like that, just putting the epoxide on there. Okay? So just keep the original structure exactly how it's written. So if I would have drawn this, even though it looks weird, it's like your cis, draw it exactly the same, okay, and just put your epoxide on there. Your epoxide can be pointing up or down. That's not the point. That's not the part that matters. It's your skeletal structure has to remain the same. Yeah, it has to be across the double bond because that's what's reacting. In this whole chapter, the double bond is what reacting. So don't ever put the epoxide over here, over here. It's always on the two carbons that have the double bond. So if I had something like this, and let's say we do this reaction here. Okay, what does that add on the double bond? An OH? Makarvnikov or anti-Makarvnikov? Anti. So do you see, here's my double bond. So I'm going to draw everything the same. Okay? Now where am I, this is where the double bond was. So I have this position and this position. So say left and right. Where do I put the OH? The right. It would come off right there. So it's always where the double bond is. There's not a double bond anywhere in this ring. It's outside of the ring. No, this is a completely different reaction. The triangle one would have been MCPBA, let's say. And then what would I put across the double bond? The triangle, yeah. The epoxide. So it just depends on what you're putting over the arrow. That's what decides your product. All the starting material, I can make the starting material exactly the same for the whole entire test. Okay? But do you see that if I put that in there versus this in there over the arrow, see how it changes completely what your product is? This one makes an epoxide, this one makes an alcohol. So it's these right here that give you basically the instructions of what your product will be. Okay, the next reaction starts off with an epoxide. So all right, so what would this make that we've been doing? Yeah, the triangle, the epoxide. And I'm going to draw it coming up, but again, you can draw it going down. Just make sure the skeletal structure is the same. Now what we're going to do is a new step, and this new step is a mechanism you might need to know. So let me just start with this starting material here, the epoxide. Now let me react this with water. And let me give you what the product will be. This is called, so looking at the product, is this a syn or an anti? Anti, one's on a wedge, one's on a dash. And this is called a diol. Why do you think it's called a diol? 2 alcohols. Where do you think, okay, comparing here to here to here, where does one of the oxygens come from? H2O. One of them comes from water. Where does the other one come from? The reactant, the epoxide. Do you see there's an oxygen there and an oxygen there? Okay, now let's look also what I have here. I have 2 hydrogens on this oxygen right now. Do any of these oxygens have 2 hydrogens? No. So this one needs to lose a hydrogen, right? So it's just an OH. And do you see this one needs to gain a hydrogen? So the first thing that's going to happen in this mechanism is this oxygen is going to gain a hydrogen. So if I draw the bonds out for water, it's going to use one of its lone pairs and grab a hydrogen off. Now when this water loses a hydrogen, what does it become? Oh, yeah. It becomes an OH. And what do you think the charge is? Negative. Okay, so let's compare this to this. Do you see that I have an OH on there? That's good. But do I want it bonded to both sides? No, I want one of these bonds to open up, right? And do you see I have an OH right here? Where do I want it? On here, yeah. So let's do this. This will make a bond right here. And what do you think happens to this? It's going to be broken and moved to where? The oxygen. Do you see that this carbon has no charge on it? So that means it has 4 bonds to it, even if you can't see them all. And when you do that, you get your final product. So write that and then I'll make sure everybody sees it. Okay, do you see that this OH made a bond right there? So I have an OH bonded right there, which is like this alcohol. And this one opened up, so it's not bonded there anymore. So I have my OH right there, and the OH that just bonded right there. Okay? If you see, I'll just put like a dotted line here. That was my epoxide right there. And it opened, this bond opened, creating the diol. So in this one, you'll need to know this reaction and the mechanism. So this is the last mechanism you need to know for this exam. So the question, I mean, you can write out the mechanism. Then you can also see, you know, I can start even from a double bond. Okay, this is the hardest I can make it. And I can say step 1, MCPBA, and step 2, add water. So what does MCPBA do? It what? The triangle, yeah. It makes the epoxide where the double bond is. So I'm just going to label this as that's step 1. And now let's do step 2 right here. Okay. If I react this with water now in step 2, what will that do? What will the epoxide right here become? OH. And what am I also adding? An OH. So the epoxide will open up as OH. And I'm adding another OH. And how will the wedges and dashes look? Opposite. And you could choose whichever one, just as long as they're opposite. Now there's only 2 more reactions I want to go over, and I like these. No mechanisms. And I'm going to combine them because they're very similar. I'm going to teach them both at the same time. KMNO4. All right, my professor always taught it this way. This one was called, we call it the good surgeon. And this one is the bad surgeon. You don't have to actually label those on the exam, but I'm just showing you right now. Okay, these are oxidizing agents. This one's a weaker one, it's a stronger one. You could tell, so if I say oxidizing agent, so oxidize, what do you think you're adding? Oxygen. Okay, do you see that this one only has 3? That one has 4. Okay, so this one's stronger. Anyway, so let's think about a surgeon. What does a surgeon do? Cuts. Okay, what have we been reacting in chapter 8? Double bonds. So what I'm going to cut is the double bond. Okay? You see, I literally just cut a hole in it. No, we're not done yet. But almost. Okay. After you have surgery, though, you need to, suture yourself back up, right? Now, these are oxidizing agents, so what do you think our Band-Aid is? Oxygen. So on both sides, put our Band-Aid oxygen. Okay, now this is the bad surgeon, and the reason is because it's very reactive. Hydrogens are easily oxidized also. Okay, hydrogen's coming off double bonds. So let's look at our starting material. Do I have a hydrogen coming off a double bond? Right here? Yeah. This will turn your hydrogen into an alcohol. So let's see what we do. It's still a surgeon, so we're going to cut just like we did above. I'm going to leave the hydrogen alone for right now. Now, before we get to hydrogen, what do I cap both ends with? Oxygen. So do you see so far it's exactly the same. The only difference is anytime you have a hydrogen coming off of there, it cuts it off. So it cuts off too many limbs, right? It goes a little crazy. And replaces it with an alcohol. So the good surgeon leaves your hydrogen foot alone. The bad surgeon takes it off. So it's a stronger oxidizing agent. So do you see that this one added 2 additional oxygens, but this one was able to add 3. And it'll put an alcohol anywhere you have hydrogens coming off of there. No, you don't have to balance them out. You just put a lot of KMNO4 in there in your beaker, and it'll just react with all your double bonds and all your hydrogens. No, let me show you, for example, what happens with ozonolysis. Also consider, I'm not showing you the side products, but in organic chemistry, we never really balance out equations. That's a waste of time, right? So Gen Chem, right? So all we care about is the organic product form. The reason is after you purify it and you get your final product, that's all that's left in the beaker. So everything else is impurities. So if I show you ozonolysis, for example, does it? Here. Okay, O3, ozone, makes this sort of transition state here. Okay, see our 3 oxygens are actually balanced for once. Okay, and then what happens is this sulfur takes off the additional one. So let me see if it ever shows it as a byproduct. No, it doesn't. Okay, so the sulfur here, that's the purpose of the sulfur in the reaction. It'll take one of the extra oxygens off, leaving you with only the 2. Okay, so there's a sulfur byproduct, but that one doesn't matter. Okay, so after you purify it, yes, that 3rd oxygen will go somewhere, and that 4th oxygen will go somewhere, but it's impurities, and once we purify it, it goes through the purification process, they'll be gone. It's just waste, sort of. They have to be there to actually react, okay? But in the end, we'll get rid of what we don't need. Okay, so those are the last 2 reactions, and that's it for Chapter 8. Let me also, because I get this a lot too, what's the purpose of all of this, right? I mean, yeah, you're learning a lot of reactions. That's cool and all. Well, there's two reasons. So I'll tell you a biological reason here in a minute. The chemistry reason. So the next, for Organic 1, for the rest of Organic 1 and pretty much the rest of Organic 2, you literally are going to learn reaction after reaction after reaction. What we're doing here is the rest of your organic life, okay? This is how you make things, okay? And this isn't every reaction ever known, okay? These are the most common ones that you're learning, okay? So they're like pieces to a puzzle, okay? So think about, I think baking might be the best analogy to chemistry, okay? So let's think about, we're going to make cookies, okay? Now, you have to know all the steps to make, let's say, a chocolate chip cookie, all right? Exactly, my favorite. So chocolate chip cookies, you need to know all the steps. You can't just start throwing things in there. I mean, if you put some peanut butter in there, it's just going to ruin the whole thing, right? You have to know to put the chocolate chips and the flour. I mean, what happens if you, leave sugar out? It'd be really gross, okay? So the thing is, there's all these different reactions, if you want. I mean, when you put things in there, you're actually reacting it. There's different steps you put in there, okay? Do we agree that the steps to make a snickerdoodle cookie is different than chocolate chip, right? Similar, but different, right? Okay? The same thing here. So all these reactions are your steps, okay? And then what you're trying to produce or make is not necessarily a cookie, but your product, okay? So this gives you not every, but most of the steps you possibly could use, okay? So I'm giving you the knowledge, and then your job as a chemist is to put them together to find that product, okay? So you have to figure out which steps, which reactions you need to get to the final product. So you could have, anybody watch Breaking Bad? At least know of it. Let me explain if you don't, and you're looking at me like I'm crazy. So he is a chemist who starts making meth, okay? So he does what we call a synthesis, and there are reactions, and we'll actually learn that reaction in Organic 2, okay? But the point is, you have to, right now, I hope you don't know how to make it, okay? I'm going to assume you don't, okay? So nobody gets in trouble. Huh? On how to make meth? Maybe. And this is all recorded, of course, so they can come back and anyway, so what happens is you need to know the steps to make it, okay? Not that I am encouraging this at all. All right, but you do need to know the steps, okay? Now, Walt, who is the main character, he's a chemist, so knows how to do it. And if you've seen it, he changes his steps. Like, he first made it one way in, like, seasons maybe 1 and 2, and then he perfected it. Now he makes, I think he calls it, like, blue ice. Yeah. So he has his new way of making it, which is better, okay? It's not necessarily cheaper because it was easier, or not easier, it was cheaper to make it with, like, the cold medicine and stuff. But it's a lot more pure, right? I don't remember what he said. It was like 99.5% pure and a lot more efficient, okay? Not cheaper, but you get a higher purity and more efficient, so you can sell it for more, okay? Anyway, but he had to know the steps, right? He had to understand them. How did he know it? His organic chemistry class. Literally, the steps you need, I mean, we haven't necessarily gone over those at this point, but we could have, but these are just some steps you could use to make other things, okay? So these are all the different things you need to make whatever chemical you want. Tylenol, okay? Let me see if I search, like, put Tylenol, because we all know it's Tylenol, synthesis. Let's go to images. Okay. Now, we haven't learned any of these reactions yet, so we will learn all of these used. But don't worry, you don't know them yet. But do you see here, they have a starting material, and then what do? They tell you what you need to put over the arrow. And that gives you a product, but we're not at the final product yet, because you need to put in something else. So this is like, we have like step 1, step 2. This is step 2, and it finally gets you the final product of Tylenol. Okay? So these steps in between here, this is what we're learning. Okay? And this one specifically, it's weird it's cutting it off. But anyway, it doesn't matter. This one's for Tylenol. And you can, any sort of, anything out there, really, anything synthetic is made in the lab. And so you're learning the most common steps used. Okay, so I'm giving you every single one of them. And then the job of the chemist is not only to know all of those, but to put them together to figure out how to get to your final product. So, there's this guy in lab. He starts off with this reactant, and he knows this is the product he needs to make. So what does he do? He consults his organic chemistry mind, he remembers every single reaction he ever learned, and figures out which steps, what reactions he needs to get to that product. Okay? So does that make sense what these reactions are? Okay, so they're the steps to make whatever product you want. Okay? And there's a lot of them. Imagine every single chemical out there. Think about everything you use. Think about every single medicine, every single cleaning supplies, food, I don't know, whatever, All of those, the steps to get to that final product, were in the lab. They use these organic reactions. Okay? Biologically, now they don't necessarily use these exact reactants. These are just like the cheapest ones we can use. Any biological chemical is expensive to buy. But what happens, so like for example, our body might not use sodium borohydride, which is NaBH4, but it'll use some other form of a hydride, and it can produce this reaction on its own. Okay? So your body, it doesn't necessarily make Tylenol, but it'll have very, very similar reactions in your body, just using something a little different. Okay? So the oxidations we went over, like the good surgeon, bad surgeon, those occur in your body, but instead of using like ozone or KMNO4, they use something else. Okay? But the same reactions occur. So it gives you an idea of things that can occur within yourself too. And then as a chemist, they usually try to find cheaper ways, to do it in the lab. Anyway, so that's what we're learning. So you can kind of see the purpose of this instead of learning, 10 reactions a chapter, and I know it gets very tedious. I took the class too, so I took 4 or 5 organic classes at least. So, I understand. I've learned so many different reactions. So it's just, again, these are the pieces to make your final product. Okay, the steps. So let's take a break, and then we'll come back and we'll review. Ozanalysis? Yeah. So you only need to know the reactions I went over. I think there's 2 or 3 extra in there. If I didn't go over it, you don't need to know it. All right, let's go ahead and start the review. Okay, we'll start with chapter 7. And let's look at degrees of unsaturation. So first, let's kind of define it. So we have a single, double, triple bond, and a ring. Degree of unsaturation. So how many degrees of unsaturation for a single bond? 0. Double, 1. Triple, and a ring, 1. So let's look at this two ways. Let me give you a structure. It's benzene. And based off this, how many degrees of unsaturation? 4. So what makes up the 4? Yeah, 3 double bonds. 1, 2, 3, and then this is a ring. We could also calculate okay, so let's calculate the degrees of unsaturation here. So how do I start that out? The equation, yeah. 2C plus 2 minus H plus halogen minus nitrogen divided by 2, not N. 2. Okay, so let's plug this in. I have 2 times what? 8 plus 2 minus, how many hydrogens? 9. Any halogens? No. Any nitrogens? Yes. What do we do with oxygen? Nothing. 2 times 8, 16 plus 2? 18. 9 minus 1? 8. 18 minus 8? 10 divided by 2? 5. So I could have you calculate it. So those are the 2 ways I could ask it. And what does this 5 tell you? How many degrees of unsaturation? So a lot, right? So I have some sort of combination of double, triple bonds, maybe a ring. Yes. Memorize this formula here. It's the only formula I'll ever make you memorize, I think. Yeah, it is. Okay, so that's degrees of unsaturation. So now let's look at naming. So let's name both of these. Okay, so let's look at this one. What's the longest chain? 1, 2, 3, 4, 5. How do we say that? Pentene. Where is the double bond? 2. So where is this branch? 4. And we call that branch methyl. So 2 pentene, methyl, 4 methyl. Now, can we decide if we could do cis trans or easy? Okay, we'll just do easy. What would this be? E, which means opposite sides. So do you see, coming off of here, I have a branch pointing this way and a branch pointing that way. What do you do when, or I guess this other one we'll look at more than one branch. Okay? So there's 2 places you could put the E. You could put it at the front, or you can put it with the 2. I don't care which one you choose. It's kind of like tomato, tomato. Yeah, it would be like that. I've also seen it as in parentheses. Okay, let's look at the bottom one. What is this? Cyclopentene. Where is the double bond? 1. Now you can put the 1 or not. I'll go ahead and put the 1. What are these branches called? Yeah, it's on the sapling they don't like 1, but it
still use 1. It just has 1 coming off of, like if you erase the lower branch, so like that one was missing, it had 1 coming off the 5th,
1 methyl.
off the 4th. So like the way it counted it's weird. You start 1 with most branches for it, right?
So what did it look like?
It was like
Was it a cyclopentene?
no, it was a cyclohexane.
And then where were the branches?
1 was coming off the right.
So like right here?
Yeah.
And the other one was?
Coming off the left top.
Here?
No, on the all the way to the left.
Here?
Yeah. It was chlorine.
Oh,
And then
a chlorine?
And then it had another methyl branch coming off. That one right there.
Here?
No, on the
So,
other one.
oh, here,
Like starting now on the left.
over here.
And it had 4.
1.
Right?
Okay, wait, you could do, yeah.
So if you went left,
1.
wouldn't it be like 3, 4, 0? It has 5.
1, 2, 3, 4,
Yeah,
5.
okay.
You have to go, that's the biggest thing, you have to go through the double bond. So,
Gotcha.
yeah, we could have either counted 1, 2, or 1, 2. And since there's already a branch right there, you're going to start that one as number 1. And probably what it hated, because, and it actually really doesn't matter, was that it doesn't want a number, probably for the double bond. I don't know. That would be the other thing that it might not like. Yeah, but counting, you always go through. So now that we know that, what are these? How many? 2? So dimethyl? Yeah, so we have to go through the double bond. So you could do either 1, 2 or 1, 2. But it won't be 1, 2, 3, 4, 5. Okay? Your double bond on a ring always takes up 1, 2. Positions 1 and 2. Now, and it's your job to figure out if you count it 1, 2 or 1, 2. In this case, it didn't matter. But over here, it did. Okay? So do you see that I have a branch coming off this side of the double bond? So if you have a branch there, that'll be your number 1. So 1, 2, 3, 4, 5. You have to go through the double bond encounter. And so these are 1 and 2. Yeah, and technically here you can write E or Z. Okay, I don't know if you have to do that on the homework. Does it tell you to? Sometimes they do, sometimes they don't. So let's look at here, but let's do it just for practice. So on this side of the double bond, I have this. Typically what you're going to see, the longer the chain, the higher the priority. So do you see here I just have a methyl, and then on this side I have the rest of the ring. So this would be number 1, priority-wise. And then over here, I have methyl or, the rest of the ring. So where will number 1 go on that side? The rest of the ring. All right, are they pointing in the same direction? Yes, so that would be the Z. There, you can put it at the beginning. Or right there. If you don't put the 1 there, then I would just put the Z up front. A lot of your rings end up being Z because this is just how you draw them. Okay, so let's practice one they have in the notes. And not necessarily naming it, but let's just say if it's going to be E or Z. So we look at everything coming off each end of the double bond. So yeah, let's look here. We have a methyl or a hydrogen. What's the higher priority? Methyl. The priorities you really only have to do when you have more than 2 branches. Okay? Chlorine or bromine. So you're looking at atomic number on the periodic table. Bromine. So how are they pointing? Opposite or the same? Opposite, so that's an E. If we're looking at stability of double bonds, is it more stable to have more branches or less branches? More branches. And what's more stable, cis or trans? Trans, because then those branches are further apart. So you want more branches, and you prefer those branches trans if you can. Okay, then we looked at E2. Here, let me put NaOH. What is the difference here? Oh, it was already made or double. We have to make stuff. That's the product, or one of the products. Okay, so here. So what if we drew like a mechanism? What do these do? What are these in general? Well, they're negative, they're bases. What does a base do? Takes a hydrogen off. And so it's going to take off hydrogen off to form the double bond. And what's my leaving group? Br in this case. Okay? Now the difference between them is where they take the hydrogen off. Where does that one take the hydrogen off? So we'll say you could do the right side or the left side. The left side. So it's going to take the hydrogen off the most substituted carbon. So I have a primary carbon and a secondary carbon. So a small base will take a hydrogen off the higher degree carbon. What do we call that product? Zaitsev. So it forms your most stable. So on this product, you would get this double bond. So between where your leaving group was and the secondary carbon. Do you see I have two branches coming off of there? Now what about this one? This one's bulky, right? Where will it take a hydrogen off? The primary, okay? The least crowded. So now my product will be this. So the double bond is between the leaving group, which was right there, and the primary. How many branches coming off here? 1. And what do we call this product? Hofmann. So know when you form the Zaitsev versus a Hofmann product and kind of what that means. So how do I know I form a Zaitsev? What do I look for? Small base. And then how do I know I form the Hofmann? The bulky base. Zaitsev is the usual product, which will be the more stable one, the one with the most branches. The Hofmann's the least stable. So it usually the double bond will usually go to the end. E2 also likes to eliminate in a certain way. So you were looking at the hydrogen in the leaving group. Does it like to eliminate it trans-like or cis-like? Trans. They want them far apart. So we've seen this. We did the analysis with the cyclohexane ring. Let me come up with one. So you can form one product here, and I want to know why only one product and what it is. Okay, so I want my leaving group and my hydrogen to be anti to each other, like trans. So what is my leaving group on, a wedge or a dash? A dash. So that means I would want a hydrogen on a wedge. So they want to be opposite of each other. Okay? So let's look at this. If my methyl's on a wedge, then my hydrogen's on a dash. This is on a dash, so my hydrogen's on a wedge. So where will the double bond form? Going up or down? Down. Because do you see that the leaving group and the hydrogen are trans to each other? They have to be. So they're 180 degrees apart. E2, there's a lot of crowding going on, so you want them as far apart as possible. So your double bond, or your final product, would look like this. So what are the two things that left in this elimination product? H and Br. So you see the bromine's gone. Did I do anything with the methyls? No. So just draw them exactly the same. And why only one product? Yeah, there's only one trans hydrogen. If this one would have been trans also, then I could have gone either way. Yeah. So that's it for the E2. So the two things we learned are to look for the Hofmann versus the Zaitsev. And then know that they like to eliminate trans. Then the final thing we learned in chapter 7 is E1. Okay, let's do two things with this. First of all, this is E1, so what do I form in my final product? A double bond. Where will I form the double bond? So here's my leaving group, or will become my leaving group. I can form it up here, which is a primary, down here, which is a primary, or over here, which is a secondary. Secondary. E1 will always form the most stable, so always go towards the higher degree. And let me just go ahead. You don't have to draw the byproducts, but this might help you with the mechanism. Okay, is OH a good leaving group on its own? No. What do we need to add to it? Hydrogen. Do you know what this is? Sulfuric acid. Is that a strong acid? It's a very strong acid. Okay, so what's going to happen? This OH is going to do what? It's going to take one of the hydrogens. So this is no longer H2SO4. What is it? HSO4. And what do you suppose the charge is? Negative. Anytime you lose a hydrogen, you become negative. Hydrogen is kind of like a positive charge. So if you gain a hydrogen, you become more positive. If you lose a hydrogen, you become more negative. Okay, so it's E1. Will I form a carbocation? Yes. What's going to leave? H2O, water. And what forms right there? Carbocation. Okay, let's look at this. Do you see that I formed one of my products right here? Water. And I'm pretty close to forming this right here. What do I need to do? Take off a hydrogen to form the double bond. What do you think is going to take that hydrogen off? HSO4 to reform itself. So it's going to take off this hydrogen. You can see the double bond forms there. So HSO4 grabs that hydrogen, and what happens to this bond right here? Yeah, it moves over to become a double bond, giving you your final product. So the biggest thing that you learn that's new is OH is a bad leaving group, so you need to make it into a good leaving group, which is water. And this is what your Lab 10 goes over, right here, the dehydration. And it actually uses 1, 2, 3, 4, well, something similar. They use 2 pentanol, which is close to the same thing, just an extra carbon, and sulfuric acid, okay? So it's almost the same exact reaction as right here. All right, so that is all of Chapter 7. So let's look at Chapter 8. Chapter 8 is mainly reaction mechanism synthesis. So let's see if we can do this, see if I can. Starting with this starting material. This is just part of the ring. Let me see if I can get all of them in. I'm just going over all of them. I'm going over every single possible reaction that could be on there. Let's see, page 4. Yeah. OAC. OAC. Close enough. So they're just going to scribble something in there that's not very legible. I can squeeze one more. Well, this isn't even all of them. No cheat sheet. Huh? I like chocolate chip. I'll be in a happier mood when I grade. I can't promise anything beyond that. Tomorrow is also Valentine's Day. What? PD palladium. Yeah. H2/PD. MCPBA is the last one. You know these, I promise, I think. If you know, if you don't, you'll know them by tomorrow, right? Hopefully. Which one? PD, palladium. Repetition. Yeah. At this point, I have pretty much every reaction in the whole entire book memorized, so prove it. That'll take a while. I could probably, literally list them all out like this. I've taught the class so many times. Yeah, it was like a puzzle. Yeah.
I'm done with that question and puts on the test. If it doesn't, on their own.
All right, let's start doing this. So if I react a double bond with HCl, what does that put across the double bond? Hydrogen and chlorine. Look what's over your arrow. Only a hydrogen and chlorine. And is this going to be Makarnikov or anti-Makarnikov? Makarnikov. How do you know that? No peroxide. So Makarnikov means what? So I'm going to just redraw that. Oops, right here. So I'm going to put the chlorine to the left or the right? To the left. It'll always go to the higher degree carbon. So if I label these, remember without the double bond, pretend it's not there, this would be a what carbon? The primary, and then this one would be a tertiary. Now, what if I have HBr with peroxide? What do I add across it? H and Br, mark or anti-mark? Anti. So the Br will go to which side? The primary side, the right side. So again, what is my biggest hint that it's anti-mark? Peroxide, right? I would ask it, I mean, I'm not going to ask all of these. I'll pick like 4 of them or something. And it'd be something like this. And well, without that. And it'll say, predict the product. What we're doing right now is predict the product. So exactly what you get here is what you would get on the exam. Now I'm like being lazy and starting with the same starting material, and I'll give you the starting material. I'll tell you, one of them does have that structure, but only one of them. This one, the reaction, that didn't give you much. But at least you know that much. At least one will start with this. Okay. What will the mercury, water, and NaBH4 do? Will it be mark or anti-mark? Mark, because there's no peroxide. And what does this add across the double bond? OH. Where am I going to put the OH then? The tertiary. So if you want, this one add chlorine, mark. This one, we added bromine, anti-mark. This one added OH, mark. And then let me actually put the hidden nitrogen here. Are these going to be like the same or opposite for wedge dash? Oh, this one's going to be opposite. So this one's a wedge, this would be a dash. So this means it adds, we call it anti, not anti-mark, but it adds anti, meaning you're going to have a wedge and a dash. Yeah, it's a dash. Here. You could just, if you put a wedge there, and then maybe just put adds anti at some way or another, just indicate. No, it's not anti-mark. It's anti-addition. Anti-mark means add your group to the least substituted side, so the side that's the lower degree carbon. That's what anti-mark means. Anti-addition means you're going to add one on a wedge, one on a dash. It has nothing to do with where you put it. Just what do your wedges and dashes look like? H3O plus. So does mark or anti-mark? Mark, and what does it add across the double bond? OH. So if it's mark, I'm going to put it right there. So add OH, mark. What's the difference between this one and this one? Yeah, which one rearranges? It was the carbocation of it. Which one forms that? H3O plus, yeah. It is more preferable because it cannot rearrange, but this one can. This one? Correct. It will not, but the one below it will. You see, it puts the OH on the same carbon, so the product is really the same, but this one could possibly rearrange into something you don't even want. What does this do? First of all, is this mark or anti-mark? Anti-mark, BH3. And then, so what will that add then across the double bond? OH. And in what position? We'll say tertiary or primary? Primary. And this one, do you remember how it adds? Does it add syn or anti? Syn, which is like a cis. So if this is on a wedge, let's say, then my hydrogen I added would be on a wedge. I think that's the only one that adds syn. All the other ones add anti. It's anti-mark. The hydrogen peroxide makes it go to the primary position. That goes to the tertiary. HBr, because it also has peroxide, will go to the primary. Anytime, I'm trying to circle it. Yeah, these are the ones that'll stand out, that'll go to the lower degree carbon. The peroxide is what causes that. The other ones will go to the higher degree carbon. What do we add across the double bond with Br2 and water? OH and Br. This one is mark. There's no peroxide. So this will be harder to decide. Which group adds second? The OH, so that's the one that adds to your tertiary. So your OH would be here, your Br is here. And does this add syn or anti? Not Makar-Markov, but just wedges and dashes. Anti. So we have a wedge and a dash. What about right here with Br2? What do we add? Two bromines. And then if one's on a wedge, the other one will be on a dash. Then here, the last, or no, there's one right here. Palladium is just your catalyst. So when I have two hydrogens, what do? It gets through the double bond and turns it into a single bond. So it turns an alkene into an alkane. And then this last one, this is one of the new ones we learned today. MCPV8 is what? Yeah, the triangle with what? Oxygen, yeah, the epoxide. So that's where the double bond was. So we're going to put our epoxide right there. And we still have 3 more reactions. Everybody have these. I'll give you a minute. Pull it up. It's already posted. I'm just basically redoing it right now. But it's under week, what, 6? 5? 5 or 6 handouts. Is it 6? So week 6 handouts. It's called like chapter 8 reactions, I think. Okay, I'm going to flip this over. And let's do the other. If there's a reaction listed on there I didn't go over, don't worry about it. Okay? Just the reactions we've done in class. Okay, so let's start back up with this. We're almost done with this part of the study part, whatever. What if, let's do this. Yeah. Everything I write on the arrow has to be there. Oh, you could do it one above, one below, or you could do both above. That putting it below the arrow doesn't mean anything different than putting it above the arrow. I could have put both of these up here. Yeah. And let me add an extra bond right here for these. Like that. It actually makes it easier for you. Okay, what does on step 1, what does MCPBA do? You form the epoxide. And then what will water do to the epoxide? Yeah, how many OHs? One on each side, yeah. So what this does, if you put both steps together, here's where the double bond was, right here and here, right? And when you react an epoxide with water, you'll get your 2 alcohols. And how do those, like wedge and dash, how does that look? So 1 wedge, 1 dash.
What were you talking about when you told me that whenever I put MCPA?
Anytime. Anytime you're making an epoxide, well, not. Anytime you're making an epoxide, you could just write MCPVA. What? Diol. Diol meaning 2 alcohols. If you have just MCPBA, that's when you make the epoxide with the ring. But if you react that, like add this extra step of water, that's when it breaks it up into the transdiols. So either you're going to have this, which is the epoxide, or have this with water, and that makes the transdiols. That's the difference between them, is the presence of that water. What does KMNO4 do? Good, bad. Surgeon is the bad one. So we had to worry about our hidden hydrogens. I did them out of order, just to confuse you. So there is a hidden hydrogen right here. This is important to label those for these reactions. So KMNO4, what does it do to the double bond? Breaks it apart. What does it cap both sides with? Oxygen. And then what does it do to the hydrogen? Makes into an alcohol. Adds even more oxygens. So you have to write both products to get full credit. So similar but slightly different. What does the good surgeon do? Same thing, except leave the hydrogen alone. So I'm going to cut up the double bond, leave the hydrogen there, and just cap both ends with oxygen. No, you don't show that hydrogen. Let's practice a couple synthesis, okay? Just so we kind of get that down. What if I have